guys, Dr. Burns here. We're going to take a look at section 1.3, which is on a topic called slope fields. Make sure your cell phone is put away and turned off so you can focus for the next few minutes. Also have a calculator handy. You're probably going to need that as we go through some of these questions. So what is a slope field? Well, you can think of a slope field as a plot on an XY plane of short line segments that represent slopes drawn at various points in the plane. So we're going to use the differential equation to draw those short little line segments and calculate slopes. So the definition here I'm looking for is slope field. And by the way, our textbook calls this a direction field. I tend to use the word slope field just because that's how I first learned it, but those terms are used interchangeably. So sometimes you'll hear me say direction field or slope field. Either one, it's the same thing. So let's do a quick example of what this looks like. The purpose of a slope field is to give us an idea of behavior about what the solutions of the differential equation are doing. So remember I said earlier on, some differential equations are very difficult to solve, sometimes impossible to solve, especially by hand. And so a slope field helps us sort of get an idea of what the solutions are doing and what that long-term behavior is. So this differential equation, dv dt, represents the velocity of an object. And so we're looking at dv dt equals 9.8 minus v over 5. Investigate the behavior by drawing a slope field. All right, so what we're going to do, and what I tend to do whenever I start these and I do these by hand, is I make a chart on my paper and I put both variables. So I'll put the independent variable, which in this case would be v. I'm sorry, t would be the independent variable. So t is the independent, v is the dependent. And then I'll do a third column for the slopes. And you can call that dv dt, or you can call it m, whatever you want to call it. So then I'll just choose literally some points on the graph. So like I said, t is the independent, v is the dependent. Now, one thing I hope you notice about this is that the slopes for this particular differential equation are only based on v. In other words, it does not matter what t is because t is not part of the differential equation. So really in this example, the t is not necessary. It's not going to do anything because it's not going to affect the slopes. I started out when I was writing the notes up for this, I put 0 here and then, oh, well, it doesn't really matter. So I'm not going to worry so much about this column, although sometimes that does matter because you'll have both variables on this side. So I'm going to worry about the v's instead. And notice I've scaled this by tens, and the reason I've done that is because we're going to divide by 5. So I just have, I have 0, and then let's do 10, 20, 30, 40, 50, and then 60 over here. All right, so if we put in 0 for v, we get, so literally going to plug this in for your differential equation and calculate the slope. So if I put in 0 for v, I get 9.8 for the dv dt. If you put in 10 divided by 5, of course, is 2. 9.8 minus 2 would give you 7.8. And that's going to follow that pattern. It's going to go down here. So this is going to be 5.8, and then 3.8, and then 1.8, and then when we get to 50, we're going to be at negative slopes, right? 9.8 minus 10 would give me negative 0.2, and then if we put in a 60, I get negative 2.2. All right, so what does this look like on the slope field? So what I'm drawing here, I'm not drawing ordered pairs. Instead of what I'm drawing at each of those would-be points is I'm drawing a little segment, a line segment, literally, that represents each of these slopes. So starting out where v is 0, that would be along the x-axis, or the t-axis in this case. And so anywhere along this axis, v is 0. And along that axis, then, my slope is going to be 9.8. So that's a pretty steep slope, right? It's almost 10. So I'm going to start off here, and I'm just going to draw a little segment that looks like it's got a pretty steep slope. And then another one, almost vertical, but it's just really steep. And so I'm just kind of hitting it at every point on the axis. And, this doesn't have to be exact. We're looking for trends. You could go in between. You can do more points, less points. Doesn't really matter. I'm just going to do every unit on the t-axis. Then when we get to 10, it's a little less steep. The slope goes down to 7.8. So I'm going to draw line segments that are still pretty steep, but a little bit less steep than the ones I drew just a second ago. All right. And then when we get to v equals 20, so along this horizontal line right here, slopes are a little less steep yet. And again, these don't have to be exact. You're just looking for trends. They need to kind of just match the trend of what the slopes are doing as v goes up here. And then at 30, so this line here, my slopes go down to 3.8, so a little less steep yet. All right, so I'm just going to kind of keep filling these in. And then at 40, we're a little bit less steep yet. Try to just be as consistent as you can. Like I said, we're just looking for behavior. All right, and then what I hope you notice is at 50, the slopes switch to negative 0.2, which of course is almost 0, but notice that they switch to negative. So I'm gonna make them go like this. Well, that's almost looks like 0. I want them to look a little bit negative, but almost flat because they're almost 0. And then when we get to 60, my slopes switch to negative 2.2. So they're negative still, but a little steeper. So they're going to be maybe more like this. And then it's just going to follow that pattern. As v gets larger, the slopes are going to stay negative, but get steeper. All right, so we're looking, like I said, for behavior. What's happening in this slope field as t goes to infinity? What's happening? And it depends kind of on where you're at, because when we look at the solution curves, whether I have a solution curve that's drawn, say, I don't know, down here versus up here, the behavior is going to be different. One thing I do hope you observe is that somewhere in between 40 and 50, where v is 40 and 50, something happens, right? Your slopes switch from positive slopes to negative slopes. So in between those, we have what's called a critical value or a critical point. If you remember back from Calc 1, what is a critical point? That would be where the derivative, remember, equals 0. So if v is less than a certain critical value, then all of the line segments we said have positive slopes in this example, and the speed of the object is increasing. If v is greater than this critical value, then all of the line segments have negative slopes, and the speed of the object decreases. And so I'm asking, what is that critical value? Okay, so let's just talk about how to figure that out. That would be where the slope equals 0. That's a bullet point there. And so that would be somewhere between v equals 40 and v equals 50. So algebraically, let's just go ahead and work that out. So that would be where dv dt, that's where critical value equals 0 would be where dvt equals 0. So I'm going to set that 9.8 minus v over 5 equal to 0. And if you solve that for v, you'll see that you end up getting, I think it's 49. Let me check my notes. Yeah, 49. There you go. So at 49, when v is 49, let's see, here's 40, so 50. So 49 would have been right up here. We would have slopes that are horizontal. So maybe like right in here. There we go. There we go. One other thing I wanted to mention, and you notice I said earlier that the behavior for this derivative, or what happens with these slopes, I guess, only depends on v. So when the slope only depends on that dependent variable, there's a special name for that. That is, and that was v, by the way, is called an autonomous differential equation. Autonomous. So in other words, if you have an equation that's in the form dy dx, or dy dt, I guess, is equal to f of y, so some function of the dependent variable. And that's what we had here. And we'll talk more about that later in the course. I just want to throw that term out there at this point. All right, so how do we graph these? And what's a good strategy for approaching these? And there's a lot of strategies. Sometimes these will be a little bit on the tedious side. We're not going to do a lot of these by hand. Some of these we're going to use technology to do, which we'll practice a little bit in class. Such strategy is called the method of isoclines. And so let's talk about what that means. The method of isoclines is a method where you look at all the points in the slope field where the solutions have the same slope, and it's some number, c, whatever that is. So dy dx equals c. A special isocline that we usually start with, and actually we did this in the last example, we just didn't call it that, is called the nullcline. So the nullcline, just like it sounds, null, often think of as nothing or zero. The nullcline is a special isocline where the slope is equal to 0. So when we're trying to graph these, one strategy is to find where the isoclines would be, and specifically where the slope would be 0, where the nullcline is, and use that as kind of a starting off. So let's try that. Let's start with the nullcline, dy dx equals 0. So in this example, I'm going to set x plus y equal to 0, and that gives me the line y equals negative x. So what this tells me is that anywhere along the line y equals negative x, I'm going to have slopes of 0. So of course y equals negative x is the diagonal line with the slope of negative 1. So what I'm going to do is I'm just going to go through and I'm going to put slopes of 0, and I'm going to pause the video real quick and come back. You go ahead and do it in your notes. Here we go. So you see that that gives me almost like a staircase along the line y equals negative x. And then just try a few other isoclines. So let's say, and it's up to you. I like to just go to 1 maybe. So we could say x plus y, that's our slope again. Where does that equal? 1. So that would be along the line y equals negative x plus 1. So anywhere along that line, I'm going to have slopes of negative 1. So y equals negative x plus 1. I'm sorry, I misspoke. I'm going to have slopes of 1. My bad. So slope is 1, right? So 1, of course, would be here for the y-intercept, down 1 over 1. So I'm talking about along this line, my slopes are all going to be 1. That's the idea. And I'm going to pause the video real quick and graph those. So there you go. You can see along that line, y equals negative x plus 1, all of my little segments have a slope of 1. And then from there, just try a few others. Say we did x plus y equals negative 1. Let's figure out where the slopes are negative 1. That would be along the line negative x minus 1. So if I go down to negative 1 and then negative 1, so like this, my slopes are all going to be negative 1. And then from there, you're kind of looking for patterns. And that's the procedure for the method of isoclines. And if you need to do a couple more, you can. We could say, where does the slope equal 2, for example? That would be the line y equals negative x plus 2. So if we go up to that and then go down 1 over 1, we have slopes that are slightly steeper than the little segments below them. And then you just kind of follow the trends from there. Now, admittedly, this is a good number of points. If I were to ask you to do one of these by hand, I don't think I would even ask you to do this many points. I'd only ask you to do a few by hand. We're going to talk in class tomorrow about how we will use GeoGebra to figure these out and have GeoGebra and Desmos. Those will do some graphs for us. But this is basically the procedure. You just set the derivative equal to different constants, look at where that would put you on the graph geometrically, and then fill in the segments according to that. I think that's pretty much all I wanted to go over with you for this video. We'll do some practice with these in class tomorrow, and we'll also look at the technology, like I said, how we can use GeoGebra and Desmos to help us do these. And we'll do a few by hand and talk about some of the behavior and the trends that we see when we graph these. So bring your notes with you, and I'll see you in class.